The next topic we are going to start is first law of thermodynamics. Okay, now first law of thermodynamics is basically based upon law of conservation of energy. Now this law of conservation of energy is such a topic which you are getting from class 8 to this engineering subject. Okay, now in this context and in this discussion we will know how this subject has evolved itself, okay, to make you understand, to make you better understand the subject of thermodynamics as it was in class 8, 9 or 11 or 12. Okay, now if you remember, as a law of conservation of energy in class 8 or 9 you have just heard about the examples, like if you rub your palm then it gets heat, okay, it gets heated. Okay, so mechanical energy is going to convert it into heat energy, or if you switch on the electric fan, the fan is going to move. Okay, this is electrical energy converting to mechanical energy. Okay, so law of conservation is such an topic which you are getting from class 8, but the depth of this subject is going to be discussed in engineering subject, which is thermodynamics. Okay, now you cannot give the examples. If someone asks you what are the examples of law of conservation of energy, you cannot put these examples, rubbing hand or switching on fan. Okay, so in thermodynamics we will go somewhat deeper. Okay, now in this case your energy will be conserved, but in a larger field, in a larger area. You are burning some fuel, you are burning some fuel, or you are giving some heat input to your system, and in somewhere in the corner of the field, if you are installing an industry or a power plant, in one corner of the field you are giving some heat, and in some another corner it is coming out as work. So to understand these fields very confidently, you need to understand this subject. Okay, first law of thermodynamics. Now first law of thermodynamics is obviously based on law of conservation of energy. Okay, and its statement is also there. What is the statement of first law of conservation of energy? Is energy can neither be created nor be destroyed, it can only be transformed from one form to another. Okay, now you can say heat and work are two different forms of same entity called energy. Okay, and this is conserved. Obviously in all other discussions which we have completed in the last videos, we have always only one motto, that we give heat to a system and we take out work from a system. Okay, you give heat and you take out work. Okay, so this heat and work is only transforming. Heat is going to transform into work. So this heat and work are going to be conserved, but these are same entity, energy only. Okay, these both two are energies, these are going to be conserved in a system. Okay, now first law of thermodynamics for closed system undergoing a cycle. So whatever the law of conservation was there, energy can neither be created nor be destroyed, it was up to the basics only. Now we need to know the first law of thermodynamics differently for processes and closed systems. Okay, processes and cycles also. Okay, so first of all we will discuss the cycle. For processes, this is going to carry some another formula other than this. Okay, now first law of thermodynamics for closed system undergoing cycle. What happens for closed system undergoing cycle? The statement goes like this: in a cycle, for a closed system undergoing a cycle, the net heat transfer is always equal to the net work transfer. Okay, now for a cycle there are certain processes. You can give some energy via pump, you can take some energy via turbine, you can give some heat is rejected. Okay, now in the whole cycle, what the algebraic sum of the heat transfer and work transfer is going to be considered. Okay, so suppose there is heat input in some process of a cycle, in some other process of the same cycle there is some heat rejection. So heat rejection is negative and heat input is positive. Okay, so algebraic sum would be there, that is heat input minus heat output or heat rejected. Okay, is going to carry the same value as net work transfer. Okay, now work output is positive and work input is positive. Okay, from some turbine you are getting some work that is positive, and via some pump you are giving the work, so this is going to be negative. Okay, so that W turbine is going to be positive, that is W turbine minus WP, that is work done by pump, it is going to be negative because you are giving some work. Okay, So W turbine minus W pump is going to be equal to Q, that means heat input minus heat rejected. Okay, that means for the whole system, whatever the heat transfer is going to be there, algebraic sum of that is summation of Q. Algebraic sum of that heat transfer, whether input or output, is going to be same as the total work transfer, whether it is input or output. So this is the formula for closed system undergoing a cycle. Okay, remember this thing very carefully. This is for cycle. Okay, and this can also be written as cyclic integration of dq and cyclic integration of dw. We have put down the caps in d, so because this dq and dw are inexact differentials. Okay, we have discussed inexact differentials in previous videos. So this same formula can be written as this cyclic integration of total q and cyclic integration of total w. Okay. Okay, so we are going to find out some results from first law of thermodynamics. Okay, so for first law of thermodynamics, we have made two cycles. From these three processes, we have made two cycles. That means from one cycle is 1A to B1. Okay, that means from 1 to 2 via path A and 2 to 1 via path B. And another cycle is from 1 to 2 via path A and 2 to 1 via path C. Okay, so A path and B path is consisting of one cycle, and A path and C path is consisting of another cycle. Okay, so after this we are going to find out some results. Okay, now if you remember what you have told in first law of thermodynamics, for a closed system undergoing a cycle, what happens is the total heat transfer is going to be equal to the net work transfer. Okay, so we are taking two cycles. Okay, for 1A to B1, that is for this cycle we are considering the equations of first law. Okay, so at one side we have written the total heat transfer, that means dq 1A2. That means from 1A2 what is the heat interaction is this one, and dq for 2B1. Okay, that is 2B1, whatever the heat interaction is there, this we have written here. Now these two consists of total heat interaction in cycle 1A to B1. Okay, now in the right hand side of this equal sign, what happened, we have written dW for 1A2. That means for 1 to 2 via path A, what is the work transfer, that is we have written here. Okay, and plus we have written here dW to B1. That is while returning from 2 to 1 via path B, what is the heat transfer, work transfer we have written here. Now these two things consists of total work interaction of this cycle. Okay, according to first law of thermodynamics, this total heat interaction and total work interaction is going to be same. Okay, now this is for cycle 1A to C1. Okay, this one, this line is for 1A to C1. Okay, similarly for 1A to C1 we have written down the same equation, that is in one side we have written the total heat interaction and the other side we have written the total work interaction. Okay, so total heat interaction is dq at 1A2, that means heat interaction is this path, and dq at 2C1, this is heat interaction in this path. Okay, and dw1A2 equal to dw1A2, that means from 1A2 what is the work transfer, and dw2C1, that is for this path what is the work transfer. So these two, this is the total heat interaction of cycle 1A to C1, that means this one. Okay, and this is the total work interaction for this cycle. Okay, we have written down two equations for two cycles, two first law equations. Okay, first law equations for two cycles. Now if you subtract first equation from second equation, you will get a result like this one. Okay, that means if you subtract this is going to cancel, this and this is going to cancel. Okay, so what is remaining, dq 2b1 minus dq 2c1. Okay, that means dq 2b1 minus dq 2c1. Similarly here dw1a2 and dw1a2 are going to get cancelled. Okay, this thing and this thing is going to get cancelled, this thing and this thing is going to get cancelled. Okay, now the remaining here is dw2b1 minus dw2c1. Okay, this is the thing what we have got here. Okay, now 2b1 and 2c1, they are having two different works. That means 2C1 and 2B1. These are two different paths. Okay. Now, as we have seen in the previous video, what we have seen that work is a path function. Okay, work is a path function means what? It depends upon the path. If there are two different paths in the same graph, then these two paths are never going to have the same network. Okay, same network is never going to be there for two different paths. So since 2B1 and 2C1 are two different paths, their work is not going to be same. Since these works are not going to be same, that means their difference is not going to be zero. If they were same, that is of same process, dw2c1 and dw2c1, this would have been same because of the same path. Now since there is two different paths, work is never going to be same. Okay, work is never going to be same because the area under these graphs are going to be different. Okay, so here what we can write? We can write that this difference is never going to be zero. Okay, now since this difference is not going to be zero, that means this difference is also not going to be zero. That means these two heat interaction for process 2B1 and process 2C1 is never going to be same. So these two also are not equal. So we have written it here, these two are also not equal. Okay, these two also are not equal. So from equation 1 we can write it like this. We are taking the same processes in the same side. Okay, suppose 2B1, dq2b1 and dw2b1 we are taking in same side, and the process 2C1 and 2C1 we are taking to other side. Okay, now you can see that whatever the process may be, this process is 2B1 and this process is 2C1. Okay, now from this thing what we can conclude that, when the initial point and final point are going to be same, initial point and final point are going to be same for same process, for the same path B and C, whether the same path, if the initial point and final point are going to be same, the difference between dq and dw are going to be same. Okay, this thing concludes that whether the process may be, whether the path may be, if the initial and final state are same, the difference between dq and dw is going to be always same, whether the process may be. Okay, that means any process, if there are multiple number of processes or infinite number of processes, the difference between dq and dw is always going to be same for all processes. Okay, undergoing a cycle, or may it not be, but if the initial and final state are same, then dq minus dw is going to be same. That means, and if you remember, for a process, if final point and initial point are same, that means what? And process are different, that means what? This quantity dq minus dw is a property. If you remember what you have said, that whether the process may be, if the final state and initial state, if any of the property is going to have, the property is going to have the definite value. So since they are equal, that means we can say that in all the processes having initial and final state same, dq minus dw is going to have some initial some definite value. Okay, some definite value they are going to have, and if there is some definite value for the constant states, that means if state 1 and state 2 are fixed, then this is known as a property. Okay, in property what we have seen that there are 2 points. Now whatever path we follow, the properties are going to be same for state 1 and properties are going to be same for state 2. Okay, now the change in these properties is always going to be same. Okay, now this property is the energy of the system. Okay, this property is the energy of the system. Okay, now this is the property. Okay, now if you take down, to generalize this without naming the processes, suppose 2B1 and 2C1, without naming the processes, what we can write? We can write that for any process, dq minus dw is equals to dE. From here, in general way, we can write this. Okay, and this is not going to, we are not going to put the cap here, okay, in D, because this is a property. We have just found out that DE is a property, and properties are always exact differentials. these caps are put when there is inexact differential. Now heat and work are inexact differentials. Okay, this depend upon paths, not on the states, but energy depends on the states. Okay, so we are not going to put d cap here. Okay, so from this we can write that dq is equals to de plus d cap w. Okay, this is the general equation which we are going to find out. Now this is the equation, this is the energy equation for a process. This is how energy is going to conserved in a process. Okay, if you are in a process, if dq heat you are giving, then it will increase the internal energy, sum of it will increase the internal energy and the remaining will come out as work. We have always said that we cannot get 100% efficiency while converting heat to work. Okay, so this is going to be the first law equation for a process. Okay, so after discussing the first law of thermodynamics for a process, that is dq equals to de plus dw, let us classify energy. Now up to this part we have seen. Okay, in our previous videos we have discussed that energy is of two types, stored and transient. Transient is what? Which can cross a boundary. Okay, energy which can cross a boundary is called transient energy. Now this comes with two categories, that is heat and work. Now new is this part. Okay, what is the stored energy? Stored energy can be classified into two different categories, that is microscopic and microscopic. Okay, so under macroscopic there are kinetic energy of the system and potential energy of the system. Okay, and in microscopic there is internal energy of the system, that is energy of the molecules. Okay, now energy stored energy, we have found out that the for a process, first law of thermodynamics is dq equals to de plus dw. Now the de is the stored energy of a system or the energy of the system. Okay, now this E consists of kinetic energy, potential energy and internal energy. Okay, these three consists of the internal energy E. Okay, so you can write E equals to Ke plus Pe plus U, that is kinetic energy plus potential energy plus internal energy. Okay, now in this equation, in our first law equation, it was written as dq equals to de, that is change in the energy. Okay, change in the energy they have said to found. Okay, now change in, now if you write down the equation for change in energy, then the change in energy will be equal to change in kinetic energy plus change in potential energy plus change in internal energy. Okay, if you undergo a process. Now for any process, the kinetic energy and potential energy are not negligible. The change of this kinetic energy and potential energy while you are going through a process, if you are going from state 1 to state 2 in a process, the change in kinetic energy and change in potential energy is very negligible. Okay, so in most of the cases, we, until and unless it is mentioned, we neglect this part. Okay, that means the change in kinetic energy and potential energy are having a value, they are not zero. Okay, but what is the change from state 1 to state 2? What is the change in kinetic energy? What is the change in potential energy? This is very negligible. Okay, so if this is negligible, then dE becomes equals to du. Okay, that is change in energy of the system becomes equal to change in internal energy of the system. Okay, now from that we can easily write dE is equals to du. Okay, now neglecting the change in kinetic energy and potential energy, the first law of thermodynamics for a process becomes dq is equals to du plus dw. Okay, so in most of the cases we take this one, dq equals to du plus dw. Okay, so we have discussed the first law of thermodynamics for a process. Okay, now for isolated system, what happens? What do you know? So for suppose in an isolated system there is a process undergone. Okay, now for isolated system the equation of first law of thermodynamics would be dq equals to du plus de plus dw. Okay, now in isolated system what happens? We know that in isolated system there is no mass transfer, no energy transfer, nothing. Okay, that means the transient energy, whatever it was going to cross the boundary is going to be 0. Okay, so for isolated system dq is also going to be 0 and dw is also going to be 0, because in isolated system there is no energy transfer and no mass transfer also. Okay, now this becomes dE is equals to 0. dE is equals to 0 means change in energy or change in energy of the system is going to be 0. That means for this the energy is always going to be constant. Okay, now for isolated system what happens, there is only rigid bottles. Okay, that means the boundary is not moving. Okay, so work transfer is 0. I insulated, that's why dq is also 0. So energy is always going to be constant in an isolated system. Such an example of isolated system would be our universe, where energy is constant for the whole universe always. Okay, so for isolated system example would be universe. Okay, the next thing would be perpetual motion machine of first kind. Okay, now here perpetual means continuous. Okay, now they have said that perpetual motion machine of first kind is a machine which will continuously give us work without taking the heat. Okay, without taking the heat they will continuously give us work. Now such type of machine is known as PMM1. Okay, now this is an impossible machine. Why? Now as they have said perpetual, that means we know it is a cycle. Okay, that we will get work continuously. That means from a cycle we will get work without taking away heat. Now for cycle, the first law of thermodynamics becomes dq summation of q equals to summation of w. Okay, that means algebraic sum of q or net heat transfer is equal to net work transfer always. Okay, now they have said that without taking the heat, so q will be 0. Now if q equals to 0, then summation of w will be also 0. From the first law of thermodynamics, for a cycle, if you don't take the heat, then the net work transfer will also be 0. Okay, now from this we can say that in perpetual machine, if you don't give the heat, the work transfer which you are getting will be also negligible. Okay, or you will not get any work. Okay, so this is the perpetual motion or PMM1 of first kind. Okay, okay, the next thing would be enthalpy. Okay, now what is enthalpy? Enthalpy is nothing but a name which is given to a term which comes to us frequently. Okay, so there is a term in thermodynamics when we do the calculations, when we derive the expressions, when we do some experiments, this term U plus PV term comes to us continuously. Okay, so to combine this, we have named this as enthalpy and it is denoted by H. Okay, so this is the enthalpy, the U plus PV term of thermodynamic relations. Wherever you are getting this U plus PV term is known as enthalpy. Okay, now this enthalpy is an extensive property. Okay, that means it depends upon the mass of the system or mass of whatever the part you are concentrating your focus on. That mass of the this enthalpy depends on the mass of that system. Okay, now if you divide it by mass in both the sides, then you will get here specific enthalpy which is denoted by small h. Only enthalpy which is extensive property, that is capital H is extensive property. Okay, if we divide it by mass, it becomes small h. Small h is specific enthalpy, that is enthalpy per unit mass. Similarly, if you here it is capital U. Okay, that is internal energy, depends upon mass again. Again, if you are dividing it by mass, then you are getting small u, that is specific internal energy. Okay, now in PV this V is capital. Okay, now if you divide it by mass, you will get small v, that is specific volume. Okay, so the specific enthalpy is going to be specific internal energy plus pressure into specific volume. Okay, again from thermodynamic relations we get that dH, change in the enthalpy, will be equals to m into Cp into del T. These are thermodynamic relations. Okay, that change in enthalpy is always equals to mass into Cp into del T. Okay, and du, that is change in internal energy of a system, is always equals to m into cv into del T. Okay, these are the very important things you need to remember. Okay, now we will find out what are the heat transfer expressions for different processes, constant volume, constant pressure, like that. For all the processes we are going to find out the heat transfer, how we are going to find the heat transfer for each and every process from first law of thermodynamics. Okay, for this, these things are very important. Make sure before going to the next topic you remember these two relations. Okay. Okay, the next thing would be heat transfer for various non-flow processes. That is, for closed system we are going to find out various heat transfer expressions for different processes. Okay, so first of all there is constant volume process. Now the first law for constant volume process is dq equals to dw plus du. We have derived it in the last board. Okay, so dq is equals to dw plus du. Now since this is constant volume means what? There is no work, as we have said in earlier cases, that for rigid tank, to get some work you have to have one of the boundary must be moving. So to have one boundary moving, the volume must not be constant. Okay, if any of the boundary is not moving, then only the volume is going to constant, and since no of the boundary is moving, we are not getting any work. Okay, so for constant volume process, dw is 0 because volume is constant. So dq becomes equals to du. Okay, now from the thermodynamic relations, what we have said that du is having a relation from the thermodynamic. What is this? This is m into cv into del T. Okay, now for constant volume process, the heat transfer will be given as mcv del T. M is mass, cv is the specific heat at constant volume, and del T is the temperature difference. Okay, that means from what temperature to what temperature we are going to take the temperature of the body, and for that how much q we need to give. That means how much heat we need to give. This relation is given by this. Okay, so constant volume process, dq equals to mcv del T. Okay. Okay, the next process will be constant pressure process. If you write down the first law equation for constant pressure process, or first law of thermodynamics equation for constant pressure process, this will be dq equals to du plus dw. Okay, now w we can write as pv. Okay, we know w is equals to, work done is equals to pressure into change in, for constant pressure process, change in pressure into change in volume. Okay, now w work we also call it as pv work. Okay, so w you can write it as pv. Okay, now as pressure is constant, it may come out, or you can directly jump from this line to this line. Whether it p comes out of the derivation or not, it doesn't matter in this derivation. Okay, now we can write, you can take the p out, or else you can directly jump from this to this. Now this is du equals to d in dpv. Okay, whether pressure comes out or not, the next relation would be like dq equals to d of u plus pv. Okay, if you take the d for all of them, you will easily write d of u plus pv. This equation or this term equals to this term, derivation of u plus pv. Okay, now if there is a term with plus sign for derivation, you can directly write it du plus d of pv. Okay, which is written here. We are just doing it in reverse way. Okay, so d equals to du plus pv. Now what is u plus pv? What u plus pv is a term which we have said that this is a term which comes to us frequently, so we are naming this as enthalpy. Okay, so u plus pv becomes enthalpy. Okay, change in enthalpy. Now from the thermodynamic relations which you have said you, there is two relations, dH and du. Now for dH, the thermodynamic relation, the change in enthalpy was given as mcp del T. Okay, so for constant pressure process, dq is also going to be m into cp into del T. So this is the way we how we can find heat transfer for a constant pressure process. Okay, the next process is isothermal process. Now equation is again going to be same, dq equals to du plus dw. Okay, now one thing we need to remember here is that internal energy is always function of temperature. Internal energy is always function of temperature. That means if the temperature goes up, the internal energy will also go up. If the temperature comes down, internal energy of that system will also come down. Okay, now For isothermal process, temperature is constant here. Now if temperature of a system is constant, the internal energy of that system is also going to be constant. Okay, but in this equation we are getting as dq equals to du plus dw, that is change in heat transfer and work transfer, and this is change in internal energy. Now since temperature is constant, internal energy is also constant, so change in this internal energy is going to be 0. Okay, change is going to be 0. So from this the final equation becomes dq equals to dw. Okay, this becomes dq equals to dw. Now dw is work transfer. Now for isothermal process, what was the work transfer we have found out in work chapter? In work chapter, for isothermal process, the work transfer was found out as constant into ln final volume by initial volume, or constant into ln initial pressure by final pressure. Okay. Now this C is what? C has come from PV equals to constant. Now this C is that C. Now this C we can write either P1 V1 or P2 V2. Okay. So you can write here P1 V1 ln final volume by initial volume. Okay. So for isothermal process, this term will give us the work transfer, heat transfer. Okay, as well as work transfer. This term will give us both these terms. Okay, work transfer and heat transfer. Okay, so next is adiabatic process. Now from the name itself, the adiabatic process, the heat transfer is always going to be 0. We do not even need to write the first law of equation. From the word adiabatic, we can easily write that dq equals to 0. Okay, so heat transfer in adiabatic process may have been only 0, but regarding this adiabatic process we have a lot to discuss. Okay, we have a lot to discuss. Now the first note which you need to know is Cp minus Cv equals to R, that is characteristic gas constant, not the universal gas constant. Okay, Cp of a gas minus Cv of a gas gives us the characteristic gas constant of that gas. Okay, now here is the proof. We know H equals to U plus PV. If you derive it in both sides, it will become dH equals to du plus dPV. Okay, now change in enthalpy, what we have found out from the thermodynamic relations. From the thermodynamic relations we have found out that change in enthalpy is mCp dt, and change in internal energy is found out as mCv dt. Okay, this is found out as mCv into dt. Okay, and dPV, and from the ideal gas equation what you can write? You can write PV equals to mRT. Okay, now if we m is constant for all the gases, I mean for the same gases this equation is written. From all the terms m is going to be constant. Now if we cancel out the m, the remaining terms would be Cp dt, Cv dt, and R is constant, so it will come out of derivative, so R into dt. Okay, now dt is also common for all the terms, so you cancel out the dt now, and if you bring this Cv to this side, it will become negative. So Cp minus Cv will give you the R. Okay, that is characteristic gas constant. So this is the proof this first law. Now in some numericals you maybe need to find out the Cp and Cv, then only you need to approach to the question. Because in some cases some students say that, sir, we did not find the value of Cp and Cv in the question, so we could not do this question. Okay, but you need to find the Cp and Cv for certain gases. Okay, now in the previous classes we have shown you how to find out the adiabatic index. Okay, how to find out adiabatic index with the relation 1 plus 2 by n. Okay, now n for monoatomic, triatomic, diatomic gases we have given. So from there you need to find the adiabatic index. Now after finding this adiabatic index, you need to find the Cp and Cv value of the given gas. Okay, for approaching to this question, because sometimes Cp and Cv are not given. Okay, so to know how to find out Cp and Cv value, we are going to approach by this. Now adiabatic index gamma is the ratio of specific heat at constant pressure to specific heat at constant volume. Okay, now from this we can write this Cp will be equals to gamma into Cv. Okay, we can easily write this. Now this, if you put this Cp equals to gamma into Cv in this equation, Okay, in this equation, if you in place of Cp you place gamma into Cv, the equation will be like this. Okay, this equation will give you this equation will come if you put Cp equals to gamma into Cv in this equation. Okay, now if you take Cv common from here, it will give gamma minus 1, Cv into gamma minus 1. So Cv will be ultimately become R by gamma minus 1. Okay, this gamma minus 1 has come from taking this Cv common. Okay, now after that, now there was a relation in mixture of gases. If you remember, we have said that characteristic gas constant into molecular weight of that gas will give you the universal gas constant. Okay, this is specific for a gas, this is specific for a gas. Now product of these two will give the universal gas constant, which is common for all the gases. Okay, now if you replace this R by the from this equation, then R will become R dash by M. So we have done what we have done, we have replaced this R by R dash by M. Okay, because sometimes R may be given, sometimes M may be given. Okay, sometimes this may be known, this may be known. So using these both equations you can find. Okay, now if this R is not given, so you can easily find it by this, because its value is constant for all the gases. Okay, 8.314, and M generally will know more than this characteristic constant. Whether we may know R or not, we know the molecular weight for some gases. Okay, suppose for carbon dioxide, molecular we know, weight we know, that is 44. Okay, so mostly prefer this equation. Either you can do, if R is given, you can find Cv from both the equations. Okay, now again from this equation we have known that Cp is equals to gamma into Cv, and this is the Cv expression. Now if you just multiply gamma with this equation or gamma with this expression, you will get the value of Cp. Okay, we will get the value of Cp. Now these are the three things we need to remember here. Okay, so I hope you have understood how we have found out Cp. Here Cp is given. Okay, Cp is gamma into Cv. Now Cv expression we have found out R dash by M into gamma minus 1. Okay, now if you just multiply gamma with Cv, we will get the value of Cp. Okay, so to find out Cp, we just multiplied gamma with this expression. It is Cv expression. We have just multiplied gamma and we have found out this. Either you can find out by multiplying gamma here also. Okay, so if you just multiply gamma into characteristic gas constant by gamma minus 1, you can also find out Cp value. Okay, so these are the expressions we need to remember to find out Cp and Cv for some gases where these are not mentioned. So you need to find it by these expressions. Okay. Okay, so now we'll see some examples of how to find out Cp, Cv for two different gases. One we are taking as air and one we are taking as helium. Okay, now it would be beneficial for us if you find the just Cv, because Cp we can find just by multiplying gamma with Cv. Okay, so for Cv, what was the expression given? The expression given was R dash divided by M into gamma minus 1. Okay, so this was the expression given. And if you put, we know that for all gases R dash is going to be 8.314. Okay, this is the expression, this is the value of R. Okay, for all gases. So divided by molecular weight, equivalent molecular weight for air. We have been telling this since every video, that molecular weight, equivalent molecular weight for air is always 29. Okay, and gamma for air is 1.4 minus 1. If you find this expression, you will get that Cv value for air is 0.718. Okay, and now what is Cp? Cp is nothing but gamma into Cv. If you can directly put gamma or 1.4 into this thing, you will get the value, or else you can find it like this way. Okay, M into gamma minus 1. You can find it this way also. So this will become 1.4 into R dash is 8.314 divided by molecular weight of air is 29 into gamma minus 1. Okay, in this way, so the value will be 1.005 kilojoule per kg Kelvin. Okay, this will be the value of Cp of air and Cv of air. You can find it like this way. Okay, now Cv and Cp of helium. Now helium is what? We have given some examples. Helium was a monoatomic gas. Now for monoatomic gas, N was experimentally, the value of N they have given to us was 3. Okay, so to find out the gamma of helium first, gamma of helium first, we need to depend upon this equation. Okay, so now helium is a monoatomic gas, so N is going to be 3. So 1 plus 2 by 3 will give you 1.67. Okay, so first of all you need to find out the gamma for helium. Now Cv of helium will go like this way, R dash by m into gamma minus 1. Okay, gamma minus 1. Now what happens? R is 8.314 divided by what is molecular weight? Molecular weight of helium goes like 4. Okay, molecular weight of helium is 4, and in place of gamma you can find 1.67 minus 1. Okay, now Cv value of gamma will be 3.1 kilojoule per kg Kelvin. Okay, this will be Cv of helium. Okay, this will be Cv of helium. R dash is common for all the gases. Molecular weight of helium is 4. Gamma we have found out 1.67 minus 1. Now Cp of helium we can find out like gamma of helium into Cv of helium. Okay, because we know that Cp is gamma into Cv. Okay, so by multiplying this you can find out Cv, or you can, if you want to find individually what is Cv, Cp of helium, you can go like this: gamma into helium into R dash divided by a molecular weight of helium into gamma of helium minus 1. Okay, so from this expression you have found out gamma helium as 1.67, R dash you have found out as this is constant 1.314, m is 4 into gamma is 1.67 minus 1. Okay, so this value you will find it as 5.2. Okay, 5.2 kilojoule per kg Kelvin. So sometimes Cp and Cv of helium maybe you need to find. Okay, so the what is the data we are having? The only thing we know for data is molecular weight and R dash. Nothing else we know. Okay, so from this giving up this equation you need to find out the expression of Cp and Cv. Gamma you need to find out if it is not given, or except air. For air we know it as 1.4. If air is not given, some other gas is given, you need to find out the gamma of that particular gas by remembering this N value for monoatomic, diatomic, triatomic. So if you know these things, you can easily find out Cp/Cv value for each and every gas. The only thing you need to know is molecular weight. Okay, and R dash is common for all the gases, so you can easily remember. Okay. Okay, so next we need to find the heat transfer for a polytropic process. Okay, now for polytropic process, again the first law of thermodynamics is same. dq equals to du plus dw. Now du we can write as mcv t2 minus t1 because it was written as mcv del t. Okay, m into cv into t2 minus t1. And the work done for polytropic process, the work transfer for polytropic process is given as p1 v1 minus p2 v2 by n minus 1, which we have done in previous video. Okay, where we are finding out the work done for various non-flow processes. Okay, so in non-flow process, for polytropic process, this was given as p1 v1 minus p2 v2 by n minus 1. Okay, n is the polytropic index which lies between 1 and gamma. Okay, that is for air it was n value was between 1 to 1.4. Okay, now here we are writing m, then we are replacing Cv with this equation, characteristic gas constant by gamma minus 1, which we have found out in last board. The Cv is R by gamma minus 1 and T2 minus T1 is constant. Okay, and this is again same. Now this we can write that m into R into T2 minus m into R into T1. Okay, m into R into T2, in the next one m into R into T1. Okay, we have written, and this one is again same. Okay, now mrt2 we can write as p2v2. Okay, pv equals to mrt, and m is constant, R is constant, and T2, that means for state 2, at state 2 temperature is T2. Okay, so in this place we can replace it by P2 V2. That means at state 2 pressure is P2 and volume is V2. Same wise we can write MR T1 as P1 V1. Okay, and this one is again same. Okay, now from these two expressions, if we take common P1 V1, if we take common, then what happens? Before this P1 V1 there is positive sign, and before this P1 V1 there is negative sign. Okay, so to avoid the negative, we are writing P1 V1 n minus 1 first. Okay, so if you take P1 V1, this term we are taking first, P1 V1 by n minus 1. So if you take P1 V1, it will come as 1 by n minus 1 minus of 1 by gamma minus 1. Okay, 1 by n minus 1 minus gamma, because negative sign is here, so we are taking it after n minus 1, minus 1 by gamma minus 1. Okay, now here we have taken minus common. Before taking common P2 V2, we are taking minus common. So if you are taking minus common, that means this negative will become positive and this positive will become negative. Okay, so if you are taking minus common, that means this term will come first, because we are taking minus common and this has become positive. So we are again taking minus P2 V2 common. So the first term will be 1 by n minus 1 and minus 1 by gamma minus 1. Okay, now in the next step what happens? These two terms are now common, 1 by n minus 1 and 1 by gamma minus 1. So these are we are taking common. Okay, after taking this common, the expression we are getting is P1 V1 minus P2 V2. By taking this common, we are getting this into P1 V1 minus P2 V2. Okay, now again the same process, we are taking LCM. Okay, LCM will give us n minus 1 into gamma minus 1. So we have written here gamma minus 1 and n minus 1. And the final sum in the denominator will give us, numerator will give us gamma minus n. Okay, gamma minus n it will give. So again now P1 V1 minus P2 V2 by n minus 1 is work done for polytropic process, or work transfer for polytropic process. So we can write that dq is equals to gamma minus n by gamma minus 1 into work done of polytropic process. Okay, now heat transfer, if you are to find the heat transfer for a polytropic process, this expression will give you the heat transfer, gamma minus n by gamma minus 1 into work done in polytropic process. Okay, W poly I have written here, that means work done in polytropic process, where n lies between gamma and 1. Okay, now in this way you can find heat transfer in polytropic process.